If you had a good category theory teacher, you probably learned that whenever you are looking at mathematical objects that are just collections of elements with some operations on them satisfying some equations, then the collection of all of those mathematical objects and the structure-preserving functions between them define what is called a category. If you had a bad category theory teacher, you probably learned that a category is just any graph of vertices and arrows between them, with a rule explaining how the arrows can be composed together. This means that a lot of stranger things form categories as well. Now it seems like pretty much anything forms a category, eh? Well, if you had a terrible category theory teacher, then you probably learned that the collection of small categories also form a category. 乐猫他讲什么废话? There's no category of categories. Strictly speaking, small categories and the functors between them do form a large category. Frustratingly, this category is actually quite nice as categories go. Locally presentable, Cartesian closed, monadic over graphs. Oh, it's not a topos though, so there's that, I guess. Don't be seduced by the cat though. Its allure leads you to the path of evil. If it's not clear why, let me explain. On one hand, objects of a category are considered the same precisely when they are isomorphic. And on the other hand, objects of a category are considered the same precisely when they are isomorphic. Okay, well, in general, two objects x and y of a category are isomorphic if we can find a pair of maps f from x to y and g from y to x that undo each other in the sense that g composed with f amounts to doing nothing on x, and f composed with g amounts to doing nothing on y. If you know what a bijection is, isomorphism is just a categorification of that. In fact, if the objects of your category have underlying sets, then isomorphic objects always have bijective underlying sets, meaning that isomorphic objects always have the same number of elements. In the alluring category of categories, the underlying set of a small category is its set of objects. This means that isomorphic categories must have the same number of objects. In an earlier video, I touch on why this notion of sameness between categories clashes with our notion of sameness of objects within an individual category, but let me try to elaborate on this a bit more by appealing to finite-dimensional linear algebra. In a run-of-the-mill general science linear algebra class, you learn about Rn and matrices. To a category theorist, this means that general science linear algebra students are working in a category where the objects are the specific vector spaces of the form Rn, and the arrows from Rn to Rm are the m by n matrices. On the other hand, a linear algebra class targeting future mathematicians talks about abstract vector spaces and the linear transformations between them. But at the end of the day, the two classes teach equivalent material. Finite-dimensional vector spaces definitionally have a finite basis, and fixing a basis is equivalent to establishing an isomorphism to some Rn. After fixing bases for two finite-dimensional vector spaces, the linear transformations canonically correspond to explicit matrices. Since moving from abstract vector spaces to Rn doesn't lose any linear algebraic information, we should expect that the run-of-the-mill general science linear algebra class works in a category that is equivalent to the category of abstract finite-dimensional real vector spaces. That said, from a set-theoretic point of view, there are far more finite-dimensional abstract vector spaces than just the standard Rn's, so these two categories cannot have the same number of objects. If isomorphisms of categories are so wrong, then what is the correct way of saying that two categories are equivalent? Well, two categories C and D are considered equivalent if we can find a pair of functors f from C to D and g from D back to C that are essentially inverses of each other, in the sense that g composed with f on some object C is naturally isomorphic to C itself, and similarly f composed with g on some object D is naturally isomorphic to D itself. These new natural isomorphisms are denoted by these double-stroke arrows in our diagrams. But gee, you say. Who cares? Why not just work in the nice category of categories and then just be sure to remember to use these weaker equivalences when comparing them? Category theory folklore gives us a way to model this approach, but it isn't as straightforward as one might naively think. If you're working in a category, and you're not just some pretentious undergrad who hasn't learned enough actual mathematics, then you're probably working in said category to leverage universal properties or the like, such as fiber products, to name a specific example. In the devilish category of small categories, the fiber product is fairly straightforward to write down. The objects of the fiber product of A and B over C is given by an object of A paired with an object of B such that the images of these objects in C are equal. Yes, I said equal. Besides my justified in a different video gripings, this construction butts heads with the correct notion of equivalence of categories. Part of the whole point of reasoning within a category and using universal properties rather than something more like set builder notation is that definitions by universal properties are invariant under isomorphism. If I have two fiber products and it happens that the components are compatibly isomorphic with each other, then from a category theorist's point of view, these two diagrams must be the same thing, and accordingly, the fiber products should also be isomorphic to each other. If we're just talking about isomorphisms, then this is indeed true and is a very straightforward exercise, but the problem is that it does not extend to the equivalences of categories. For a concrete example, we need two ingredients. The first player is a category I like to call Neo. It has exactly one object, and the only arrow it has is the identity arrow on said object. Player 2 is called the walking isomorphism for reasons that have to do with the evil category of small categories. This category has two objects, bottom and top, and besides the identity arrows, the only other arrows are an arrow lambda from bottom to top and an arrow rho from top to bottom, which are inverses of each other. It turns out that player 1 and player 2 are the same thing. The unique functor from the walking isomorphism to Neo is an equivalence of categories that is notably not an isomorphism of categories. On the other hand, there are two functors from Neo back into the walking isomorphism. One sends the unique object to the bottom object, and the other one sends it to the top object. While the bottom and top objects are isomorphic, they are not strictly equal, so if we consider the fiber product of Neo with itself over the walking isomorphism, the result is the empty category with no objects. If this feels wrong, good, you're not evil. Since Neo is equivalent to the walking isomorphism, we should expect to be able to replace the walking isomorphism with Neo and get an equivalent fiber product. However, the fiber product of Neo with itself over itself is, well, itself. This means that depending on our presentation of the diagram, the fiber product is either the empty category or Neo. And since there is no functor from Neo to the empty category, these categories cannot be equivalent, not even isomorphic, showing that the fiber product as defined here is not invariant under equivalence of categories. So how do we fix this egregious shortcoming of the fiber product of categories? Well, I think I already alluded to it. All we have to do is replace this strict equality with an isomorphism. This is still just hand-wavy set builder notation though. If we want a universal property, the property is that we have projection maps to A and B just like before, but rather than making a square commute, which would require talking about equality, what we get is that it comes with a canonical natural isomorphism from the upper right path of the square to the lower left path. I don't want to elaborate on this, but defining the fiber product in this way ensures that it is invariant under equivalences of categories as we would expect. But gee, the inquisitive among you may be wondering, why not just formally invert the weaker equivalences of categories so that they are isomorphisms? Then we can just do ordinary category theory again. While simply turning arrows into isomorphisms might sound like a tall order, this is a standard construction in category theory. If you take some category C and look at some set W of arrows in that category, you can try to create a category C adjoin W inverse called the localization of C at the set W, which is universally characterized by the property of being C but with the arrows in W turned into isomorphisms. Of course, I say try because it can really upset the set theorists. Luckily for us, we don't have to go through this awful construction and butt heads with the set theorists. All we have to do is replace functors between categories with natural isomorphism classes of functors between categories. This localization is called the homotopy category of categories. By design, the isomorphisms in the homotopy category are exactly the equivalences of categories, so this is a genuinely good category. So back to the question, why not just work in this category? Well, while this is a perfectly good category with no evil connotations, the homotopy category suffers from a minor complication. It's very ugly. It doesn't even have all fiber products. You can find an example of a fiber product that does not exist in the homotopy category on the NLab. The only thing I should warn you about, though, is that as of recording this video, that example is wrong. It really grinds my gears when public content for mathematics is just wrong. I mean, you know that tons of people are going to be reading it. Why can't you just do the tiny bit of due diligence to make sure that your work is correct? It's really not that hard. Here's an example brought to you by the letter G. The G stands for group, because this example will require a bit of elementary group theory. If you don't know what a group is, don't worry. It's just a groupoid with one object. I'm not joking. We'll be looking at categories of the form BG, where G is a group. This is a category with one object, where the arrows of this object to itself correspond to the symmetries in the group G. Now, I claim that the fiber product of these three categories of that form does not exist in the homotopy category of categories. In this diagram, S3 denotes the symmetric group on three elements, and A3 is the alternating subgroup. The functors in this diagram are just given by inclusion. If you don't know what any of that means, S3 is also the group of symmetries on an equilateral triangle, and A3 is the subgroup of rotational symmetries on said triangle. Now, before we think about the homotopy category, let's do a couple of warm-up rounds, starting with what is the fiber product of this in the category of categories? If you don't need this warm-up, then you probably already know that the fiber product in this case is just the intersection of BA3 with itself as subcategories of BS3, giving us BA3 back again as the fiber product. I could leave it at that, but I'm worried that this makes too much intuitive sense, so let me belabor the point a bit more. Let's denote this strict fiber product by L. First, let's figure out why L must have exactly one object. Well, we can access individual objects of a category C by looking at functors from Neo into C. All you have to do is take the unique object of Neo and send it to whatever object of your category you're interested in. This means, by the universal property of L as a fiber product, that an object of L corresponds to taking an object of the first BA and an object of the second BA, such that these two objects are exactly equal in BS. That is, this is just the intersection of objects. Since BA and BS both only have one object, this means that L must only have one object as well. This means that L is isomorphic to BM for some monoid M. If you don't know what a monoid is, it's just a group where you can't necessarily invert the symmetries. Every group is a monoid, and the distinction between monoids and groups doesn't play a very major role today, so you can make believe that I'm just talking about groups if it helps you sleep at night. Of course, if none of this is making sense to you, then this video is already helping you sleep at night, but I digress. Anyway, to get at understanding the monoid M, we need a way of accessing its elements. For this, we use the natural numbers under addition. Thanks to induction, monoid homomorphisms from the natural numbers into M are completely determined by where they send the number 1. By delooping, the same thing can be said about functors from B of the natural numbers to B of M. Once again appealing to the universal property of L, now written as Bm, this tells us that an element of M corresponds to picking out two elements of A3 that are exactly equal as elements of S3. In other words, this is just the intersection of A3 with itself, which is why we just get A3 back. Okay, that's the first warm-up. The second one is to calculate the correct fiber product of these categories. While it is indisputably justified to call this the fiber product, this is potentially confusing with the categorical fiber product in the category of categories and what's about to be the homotopy category of categories. So let me just call this the derived fiber product and put an R in the notation to hopefully avoid too much notation overloading. As I've mentioned already, the derived fiber product requires providing an explicit isomorphism between these two objects. So even though BA3 and BS3 both only have one object, the fiber product construction gives us one object for every symmetry in S3. This means that the construction is giving us 6 objects. On the other hand, the arrows of a general fiber product are given by compatible pairs of arrows in the factors. Spelling this out in our specific case, if I have two objects sigma and sigma prime, an arrow from sigma to sigma prime is given by a pair of symmetries lambda and rho in A3, such that lambda times sigma is equal to sigma prime times rho. If you work it out, this means that the fiber product has two isomorphism classes of objects. The first is the class of the symmetries of S3 that are also elements of A3. The other isomorphism class is given by the symmetries that are, well, that are not of this form.
Hell no!
I'm just kidding. This partition is constructive. Interestingly, while these two objects are not isomorphic to each other, they do have the same automorphism group. In other words, the derived fiber product can be decomposed as two copies of BA3. Alright, I hope you're warmed up. Let's see what happens when we look in the homotopy category. I claimed that this diagram does not have a fiber product, so let's suppose I'm wrong, because that's never happened before, and that there is a fiber product. Let's call it P. By definition, since the homotopy category is just another ordinary category, the fiber product P is universal with projections onto the two copies of BA3 that make this square strictly commute. But by definition, strictly commuting in the homotopy category means that there exists a natural isomorphism from the upper right path to the lower left path. But gee, you may think, wouldn't the derived fiber product satisfy this universal property? The two notions are definitely similar, but the difference is that in the derived fiber product, the natural isomorphism is part of the data, whereas the homotopy category only requires that at least one such natural isomorphism exists, without pinning down a specific one. Suppose I have some category C that forms a commutative square in the homotopy category. As I just explained, this means that we have a natural isomorphism theta connecting the two paths. The universal property of the derived fiber product says that there is an essentially unique functor from C into the derived fiber product, along with some natural isomorphisms between the induced triangles, such that the pasting diagram of the natural isomorphisms compose to give back theta. It's not important that all of those words made sense, but in the homotopy category, this means that the commutative square with C induces a functor into the derived fiber product that makes the induced diagram strictly commute. This is almost the universal property of the strict fiber product in the homotopy category, but the catch is that we lose the uniqueness on the induced functor. This is because the uniqueness of the universal property is also tied to the natural isomorphisms in the picture, but the homotopy category doesn't care which natural isomorphisms you use. In any case, the derived fiber product and the fiber product in the homotopy category are undoubtedly very similar. This existence but not necessarily uniqueness property is called a weak limit on the NLab. But given how this is overlapping with higher category theory, where the word weak is a bit overloaded, this universal property without uniqueness would probably be more appropriate to be called a versal property. This versal property gives us a functor v from the genuine fiber product P into the derived fiber product. But then also by the universal property of the fiber product P, the derived fiber product also admits a unique functor u back into P. What's more, if we combine these two functors together, we get a functor from P back to itself. But the uniqueness condition on the universal property of P kicks in to tell us that this composite functor must be naturally isomorphic to the identity on P. In fancy categorical jargon, this is to say that the fiber product P is a retract of the derived fiber product. This was a fun aside, but this still doesn't tell us what the fiber product would have to be, so let's start by figuring out how many objects P should have. Thinking back to when we worked with the evil category of categories, we saw that we can identify objects of a category with functors out of Neo. Since now we're looking at functors up to natural isomorphism, these arrows mapping out of Neo in the homotopy category classify isomorphism classes of objects. While this is not strictly the same thing, it's good enough for our purposes. The same argument as before implies that this fiber product P must have one isomorphism class of objects, and therefore P is still equivalent to a category with exactly one object. Since equivalences of categories are isomorphisms in the homotopy category, we can freely replace P with Bm for some monoid M, just like before. So that's the objects down, but how about the arrows of P? In the evil category of categories, functors from B of the natural numbers into Bn correspond to the actual elements of M, but now we only get these elements up to natural isomorphism. In this context, natural isomorphisms correspond to conjugation by an invertible element of M. Therefore, in the homotopy category, rather than getting all of the elements of M, we only have access to conjugacy classes of elements of M. We should first figure out what the conjugacy classes in A3 and S3 are. On one hand, since A3 is an abelian group, every element is in its own conjugacy class. On the other hand, the conjugacy classes of S3 correspond to the identity, the transpositions, and the 3 cycles. Notably, conjugacy classes of A3 only map into the identity and 3 cycle classes of S3. Now, appealing to the universal property of the fiber product Bm, the conjugacy classes of M must correspond to pairs of conjugacy classes in A3 that map to the same conjugacy class in S3. With a little bit of counting, this tells us that M must have 5 conjugacy classes of elements. While this doesn't tell us a whole lot, it does tell us that M must have at least 5 elements. Now, let's use the fact that Bm is a retract of the derived fiber product, and the fact that the derived fiber product is given by 2 copies of Ba3. Since Bm has only one object, any functor into the 2 copies of Ba3 must factor through exactly one of them, so we actually get that M must be a retract of A3 up to conjugation. This means that U composed with W must be an inner automorphism of M, which implies that the map W from M to A3 must be injective. In other words, M is actually a subgroup of A3. Injectivity is already enough to derive a contradiction, because A3 only has 3 elements, and we just said that M must have at least 5 elements. Et voila, contradiction. This means that the original diagram cannot have a limit in the homotopy category after all. If you're still here, thank you for watching, and mad kudos to you. This video was a lot more technical than I intended. If you liked what you watched, that gives me a lot of joy, because these kinds of cute examples are something I really loved to do when I was a grad student. Anyway, if you didn't like what you watched, I guess I'm not that surprised, but it's fine. The fans who've got my back will always form a versely terminal object in the category of sets.